Hello, good morning, everyone. I hope you all are doing wonderful and are in your good health. So, today we are going to start our lecture, which is about concurrency in modern hardwares. So, first of all, about the concurrency, as we know, like concurrency in modern hardwares and in system level programming, this one refers to the ability of a computer system like to execute multiple tasks or processes simultaneously. So this gonna includes in the breakdown in different sectors like in the multiple cores, multi-threading, parallelism, context switching, and synchronization. So here we have example, as you can see here. So like you can see here this one. So this one is actually like we have to break down this one. Like first of all, we have to defining the function in this one. Like you have like two functions defined with foo and bar. And so these are the tasks like you want to run concurrently. So then the step two is like starting the main function like here you can see. So the in this one the main and like this one the function actually like you can say orchestrates like the concurrent execution of foo and bar. Then we have to starting the thread like like you start two separate threads for the function foo and bar, so this allows them to run concurrently like here you can see start the thread foo, start the thread bar, you can see here. Then after this one we have to waiting for the threads to finish, like after the starting the threads, the main function waits for the both threads T1 and T2 to complete their execution before proceeding. So then we have to wait until it's finished T1, like this pauses the execution of main, like until the thread running on full like T1 is finished. So then like after this one, we have to also wait like here. We also have to wait until the finished T2, like this pauses the execution of the main until the thread running bar on the second one, like T2 is finished. Then we have to like resuming the sequential execution here. You can see here like once the both threads T1 and T2 have finished, the main function resumes the execution. So at this point, there is no concurrent execution anymore, like in the mains which runs sequentially. So after this one, we can say through this example, like how this like how does a CPU actually do this? It's very simple. Like the CPU manages this program like by creating threads, context switching, running the task, synchronization, and also the sequential execution. Because this efficient management and execution of threads enable the concurrent processing and synchronized completion of tasks. Then after the next one, like how the concurrency be used to make your program faster. So this could be like concurrency can makes your program faster, like by allowing multiple tasks to run simultaneously. Like it would be like parallel execution. It would be through efficient resource utilization, improved responsiveness, and also the task decomposition as well. So this is actually a simple and a short answers to these questions through the example. Then we have to move the next one. When we move to the next one, we see here and the detailed of the concurrency in modern hardwares. So as I told you, like by breaking down the concurrency in modern hardware, because this refers to the ability of computer systems to execute multiple tasks or processes simultaneously. So this could be like in this one, and this is going to break down into multiple cores, because modern CPUs have multiple cores, like each core handle its own tasks independently. So this means the computer can run several programs at once without slowing down. And also it includes the multi-threading, like within a single program, tasks can be divided into smaller parts, which we used to call the threads, because these threads can run at the same time, sharing the CPU's resources efficiently. And also it could be like a parallelism, because the when the tasks or the threads are executed at the same time across multiple cores, it's called parallelism, because this speeds up like the processing and improves performance as well. And also in in concurrency, it includes the context switching as well, because the operating system switches between different tasks quickly, giving the illusion that they are running simultaneously. So this is very much crucial for multitasking. So I would say like a concurrency in modern hardware and system level programming. This allows like for more efficient and faster processing by utilizing multiple cores and threads, managing the tasks simultaneously, and also ensuring the coordinated access to the resources as well. Then we have to move to the next slide, which is about simultaneous multi-threading, which we used to call SMT. And this is also known as like hyper-threading. So this is actually a technique which is used by modern CPUs to improve the performance by allowing multiple threads to run simultaneously on a single physical core. So first of all, like how this SMT works, and this gonna works like through the multiple logical cores, because each physical core is treated as a multiple logical cores, like it could be usually two. So this means the operating system sees the more cores than are physically present. And it also works as a shared resources, like the logical cores, which gonna share the physical resources of the single core, such as caches, execution units, and the registers as well. And also I would say how it makes the program faster, and then this could includes the efficient utilization as well. like uh, when one thread is stalled, waiting for that data from the memory, so another thread can utilize the execution units, because this keeps the core busy and improves like overall throughput as well. And there are a lot of benefits for SMT, and the benefits gonna include, I would say, because of its increased throughput, its improved resource utilization, better handling of the concurrent as well. So these all are the benefits we can get from SMT. Then through this one we're gonna move to the next one, which is about the problems with SMT. So here's we have the problems with the SMT. In SMT, while beneficial in many ways, there also come several challenges and the potential drawbacks as well. So some of the problems or the drawbacks or the challenges we're gonna face is about their. Now, the first one I would say is about their resource contention. Resource contention includes their shared resources, of course, because the logical cores share the physical resources of the CPU, such as caches, execution units, and the memory bandwidths. So when like multiple threads compete like for these resources, the contention can occur, which gonna leading us to the suboptimal performance. And also their cache tracing, if the threads have a large and different memory footprints, they may constantly evict each other's data from the cache, which gonna causing the frequent cache misses, and also the reducing its performance as well. So the number two problem or like the drawback would be its security vulnerabilities. It's gonna includes its side channel attacks, because the SMT gonna increase the risk of certain types of security vulnerabilities, like such as side channel attacks, because these attacks exploit the shared nature of CPU resources to their infer sensitive information from other running threads as well. So the next one could be it's in the security vulnerabilities includes their spectrum meltdown, because some variants of these speculative execution vulnerabilities are more easily exploited on CPUs, with SMT enabled. So as the shared resources provide additional channels for the attack. And also the problem could be its uneven performance gains, which gonna include its workload dependencies, non-parallelizable tasks, and also its the fourth problem I gonna add, which is its complexity in software optimization, which includes its thread scheduling, because the operating system scheduler needs to efficiently allocate and manage the threads across logical and physical cores. So poor scheduling can negate the benefits of SMT. And also it's performance tuning as well, like the developers are gonna needs to optimize their software specifically for SMT, which can be complex and time consuming. So this includes ensuring that threads do not excessively compete for the shared resources, and it also includes its power consumption and the heat as well, because running the multiple threads like on a single core going to increase the power consumption and the heat output of the CPU, which might require better cooling solutions as well, just because of its excessive heat generation, which this also going to leads to the thermal throttling, like where the CPU reduces its clock speeds to prevent overheating, and also negating that like a performance benefits of the SMT. So these are the potential problems or the drawbacks we're gonna face with the SMT. There are a lot of others you're gonna edit in these as well. So it's very much like to understanding these problems. It's very much important for us to and all the developers and the system architectures to effectively leverage the SMTs and mitigate its potential drawbacks as much as we can. Then the next slide includes the cache coherence. So cache coherence actually refers to the consistency of data stored in local caches of a shared resources. So in a multi-processor systems, each processors may have its own cache and keep these caches like synchronized in a crucial to ensure data consistency. So the first question arises in your mind, like why the cache coherence is important. So, like, why it is important? Like, I would say, in a multi processor systems, each processor can have its own cache. Like, when the multiple processors or the cores work with the shared data, they may have like stored copies of their data in their respective caches. So, without a mechanism to keep these cache coherent, the processor might end up working with like stale or like I would say inconsistent data, which gonna lead us to the incorrect programming behavior. So the next one I would say about the cache coherence protocol, which gonna includes like the main types could be it's the write invalidate protocols, write update protocols, and all these are its types. So the next one, and this is all about the cache coherence. If you got any problem, then you please ask me, okay? Don't hesitate to ask any question. So then we are moving further to the next one, which is about the messy protocols. This is widely used right to invalidate the protocols that uses like four states to manage the cache lines. The four states could be with its name through its name like messy, it's modified, exclusive, shared, and invalid. So the first of all, I have to describe the modified, and this is actually the cache line which is modified and is only in the concurrent cache. So this one actually copy in the main memory, which is stall. And the next one is about the exclusive. The cache line here is only in the concurrent cache and is not modified. So the copy in main memory is up to date. The third one, which is about the shared, so the cache line may be in the other caches and is not modified. So the copy in main memory is actually up to date as well. The last one is about the invalid. In this one, cache line is not loaded, so the cache line here is invalid and must be fetched from the memory or another cache. So this is all about the messy protocols. Then we have to move further to the messy protocols to the next one, which is about the memory orders. So here for the memory orders, we can see here this one actually refers I would say to a sequence in which memory operations load and stores are executed and perceived by various threads or the processors in a computer system. So by understanding the memory ordering is very much important for writing the correct and efficient concurrent programs. So different architectures which gonna may have different memory models which gonna define the rules like how memory operations gonna be recorded. So this memory order gonna some of the key concepts of the memory ordering gonna includes the memory model, because the set of rules for this one defining how many operations about the read and write are ordered and observed by different threads, which gonna be include some common models in this one, like the sequential consistency and also the relaxed consistency. The next one I would say in the memory order could be its reordering, because the CPUs and compilers may reorder the instructions to optimize its performance. So memory ordering ensures that these optimization do not leads to the incorrect behavior in any concurrent programs. And also some of their barriers and the fancies, like some of the instructions that prevent the reordering of the memory operations across them, so they actually used to enforce the specific memory ordering, which gonna be its memory barriers, acquire and release semantics. So these all are the like I would say in the barriers and the fancies gonna include these ones. So then this one we're gonna see some of the weak and the strong memory orders, like here. So memory ordering, and which is actually also known as memory consistency. So this one defines the rules, like I would say, that governs the orders in which memory operations, like loads and stores, which gonna be appears to executes the other processors or the threads. So this is very much critical and important in multi-threaded programming, because different processor might see operations occurring in different orders unless any kind of strict rules are enforced. So first of all, let's discuss about a strong memory order. So for this one, strong memory ordering actually ensures that the memory operations are seen in the order they were issued, by providing a more intuitive and predictable behavior for the programmers. And also their main characteristics of strong memory model gonna include some sort of like sequential consistency, and their total store order, which we used to call TSO. And also the next one, which is about the weak memory order. So this one allows more flexibility in the reordering of memory operations to improve the performance. However, I would say it requires the programmers to use the synchronizations mechanisms to ensure correct behavior. So the characteristics for the memory, for this one, the weak memory ordering gonna includes its relaxed consistency model, load or the load store, which includes the reordering, like a read and writes gonna be reorders like with the respect of other read and writes, by allowing like for higher performance and optimization. And also this gonna includes like its explicit memory barriers, because we must say like we're gonna use the memory barriers or the fences to enforce specific ordering when needed. So these barriers prevent certain types of reordering to ensure data consistency. So this is all about the weak and strong memory orders. And then let's jump to the next slide, which is about the memory barriers. So this memory barriers, also sometimes call this one as a memory fences. This is a very crucial concept in concurrent programming, because they are very much and they are actually a special I would say instructions that prevent certain types of reordering of memory operations, by ensuring correct execution order and also the data consistency across different threads and processors. So first of all, the question arises in your mind is, what are memory barriers? So memory barriers actually are instructions that enforce the ordering constraints on memory operations, like loads and stores. So without barriers, compiler and CPUs might like reorder memory operations to optimize their performance, which gonna leads to the inconsistent and incorrect behavior in concurrent programs. So there are some types of memory barriers, like it gonna includes the load barriers, which we used to call the read barriers, store barrier, which is write barrier, full barrier, which is actually a memory barrier, acquire barrier, release barrier. So these all are like I would say like the types of memory barriers that we were going to discuss in today's lecture. Through this one, through the memory barriers, we are going to jump to the next one, which is about the atomic operations. Atomic operations are low-level, indivisible operations that are completed in a single step relative to the other threads. So they are very much crucial in concurrent programming to prevent any kind of race conditions and ensures the data consistency without the need for complex synchronization mechanisms like I would say locks. So for this one, an atomic operation is very important. Like I would say, this is that operation that runs the completely independently of any other operations and cannot be interrupted. So this means that once an atomic operation starts, it runs to the completion without any other thread being able to observe it like in an incomplete state. So I would say the common atomic operations gonna include atomic read write, which is like reading or writing a variable in a single or indivisible operations. Atomic increment decrement, like incrementing or decrementing a value without the interruption. And this is very much important, which is about atomic compare and swap, CAS. This one we're gonna discuss in the next slide. Like compares the value of a variable like with a given value and like only if they match, and it's also gonna swaps it with like a new value. So this is a fundamental building block for many synchronization algorithms. And also this one includes atomic fetch and add, like this one like in this one which atomically adds a given value to a variable and returns the original value of the variable before the addition. So there are a lot of benefits of atomic operations. I would say the main benefits could be its performance, its simplicity, and its avoiding any kind of deadlocks. So this is all the like I would say benefits of atomic operations. So through this one, we're gonna move to the next slide, which is about the compare and swap operations. This is very much important atomic operation, which is used in concurrent programming to implement any kind of synchronization mechanisms and logs-free data structure. So it allows a threads to update a variable like only if it matches an expected value. So by ensuring safe updates like without requiring any logs. So this compare and swap is an atomic operation that performs like the compares like in the compares the current value of a variable with an expected value. If the current value matches the expected value, it swaps the current value with a new value and then it returns to the original value of the variable. So like in the CS operation, the steps could gonna include it's a load current value, like if this one gonna load the current value of the variable, then compare it, like which gonna compare the current value with the expected value, and then it swaps it. Like if the current value matches the expected value, this one gonna sets the variable up to the new value. If it does not matches the expected value, do nothing. Then it's gonna return to the original value of the variable. So through this one, compare and swap, we're gonna see here, you can see here, and this is the conceptually work I have done here. So let's break down into the steps like I would say, here I have discussed it in further details. Like here you can see, this is how it typically looks like. So in the step one, which gonna like load the current value, here you can see which gonna load the current value. So in this one this gonna load the current value for variable a into the expected like here. So in the step 2 and 3 like here you can see this one is about compute the new value which is desired, which is actually based on the current value and expected like using a non-trivial operations. So the step 4, which is about the attempt CAS, like here in the last you can see. So in this one attempts to like atomically update A to a desired if A is still equal to the expected one. If A was modified by another thread between step 1 and step 4, so the CS operation will fail and success will be false. So the fourth one, I would say that like in this one, we have to repeat until it's successful. So the while like which is about node success in the step 5, you can see here. So loop ensures that if the CS operation fails because A was changed by another thread, the steps are repeated until the CS operation succeeded. So in the essence, I would say this loop repeatedly tries to atomically update A to a new value by computed from its current value and also ensuring the thread's safe update without using logs. Then we have to jump to the next one, which is about the parallel programming. Here we have the parallel programming. This is actually a type of computing, like where many calculations or execution processes are carried out simultaneously. So it leverage multiple processor or cores to solve the problems, like to foster by dividing the task into smaller subtasks and running them concurrently. So the key concept gonna include it's like the concurrency or the parallelism, because the concurrency gonna managing the multiple tasks at once but not necessarily simultaneously. So it's about dealing with like a lot of things at once, but the parallelism is performing the multiple tasks simultaneously. So it is about doing the lot of things at once as. So the next one, I would say the key concept is about its granularity, because it's gonna include its like the coarse grained parallelism, because the large tasks are divided among processors, which gonna overhead due to their communication and synchronization is very much relatively slow. Then it could be like it's fine grained parallelism, because the small tasks are divided among the processors and the higher communication and synchronization overhead as well. And also going to include task decomposition, and there are a lot of benefits, I would say, for the parallel programming. And the benefits gonna include like its increased performance, their efficient resource utilization, and also their scalability as well. But with the benefits, there are some sort of challenges we're gonna face, which is about its like synchronization, their load balancing, their communication overhead, their debugging and testing. So these all are the some sort of benefits or the problems or the challenges we're gonna face in parallel programming. So let's move to the next one, which is about the mutual exclusion. So mutual exclusion is actually a fundamental concept in concurrent programming, which is used to prevent multiple threads or processes from simultaneously accessing a critical section of code that manipulates shared resources. So this helps to avoid race conditions and ensures the data integrity. So first of all, what is mutual exclusion? As I told you, and this one is like this one ensures that like only one thread or process is gonna access a critical section, which is a part of the code that access the shared resources at a time. So by enforcing the mutual exclusion, we prevent conflicts and inconsistencies that gonna occur when multiple threads try to read or write the shared data concurrently. So why this mutual exclusion is important? Uh, this one is important, I would say, to preventing race conditions, to ensuring the data integrity, and also to providing the safe synchronization. So these are, I would say, like kind of like its benefits or why it is important, and we're gonna add these three things in the mutual exclusion. So then we have to move to the next one. Here we can see this is about the logs. Logs are actually synchronization primitives, which is used in concurrent programming to ensure that only one thread or process gonna be accessed like at a critical section of a code at a time. So this one helps to prevent the race condition and ensures the data integrity, like when multiple threads attempts to read or write the shared resources simultaneously. So these logs have some sort of types, which gonna includes the mutex, as we discussed, like the mutual exclusion, the recursive log, which we also call it reiterant log, and also it includes the read write log and spin log. These all are the like the types of the logs that we are going to discuss. So through the logs we have to here is about the shared logs. So this is also known as I told you, this is a type of a log. This is also known as read and write log. So this is actually a synchronization mechanism that allows the multiple threads to read a shared resources simultaneously while ensuring that only one thread can write to the resources at a time. So this type of lock is useful in scenarios like where read operations are much more frequent than the write operations, which gonna allowing for better performance and resource utilization. So the main characteristics for the shared logs is about its shared log, which is about read, its exclusive log, which is about the writing, and some sort of advantages I have to count is it's because of its improved performance and also its flexibility. But with the advantages, there are some sort of disadvantages as well, because of the disadvantage could be its complexity or the potential for starvation. In this one, I would say like the writers may starve, like if there are any kind of constant readers, is that like a write log will only be granted when there are no readers. So let's move to the next one, which is about the problems with mutual exclusions. So this is very much essential for ensuring the correct behavior of the concurrent program. It also includes like and going to introduce several challenges and potential problems. So first of all, I have to add the first problem, which is about its dead logs. So in the deadlocks, this one occurs when two or more threads are waiting for each other to release the logs. Here you can see in the example, thread 1 and 2, so which gonna causing all of them to be blocked indefinitely. Here you can see this when the two threads are here waiting for each other to release their logs. And like here you can see like a thread 1 holds the log A and B and waiting for the log 2, while the thread 2 holds back the like a log 2 and waits for its log 1, I would say. So the next one about it's is about I would say about starvation, because in this one I would say is actually about the high contention on a mutex, which gonna leads to the some threads and making no progress, and also gonna be partially be elevated by using less restrictive locking schemes. And also the problem could be its contention, because contention gonna occurs in like multiple threads frequently attempts to acquire the same lock, leading to the performance degradation due to overhead of the managing the lock. And also the problem with the mutual exclusion, this one gonna include its priority inversions. Because a lower priority thread holds a lock needed by a higher priority thread, which is gonna causing that higher priority threads to be blocked while the lower priority thread continues to execute. So this is actually I would say the problems with mutual exclusion we're gonna face. So let's jump to the next one here, which is about hardware assisted synchronization. This one refers to the like using specialized hardware features to manage the synchronization between multiple threads or processes, and also improving the performance and reliability in concurrent programming. So these hardware mechanism provides the atomic operations like that are essential for implementing logs, semaphores, and like any kind of other synchronization primitives as well. So some of the like about the key hardware assisted synchronization mechanisms gonna include its atomic instructions. Like in atomic instructions are indivisible operations that complete without interference from other threads. So they are fundamental for building synchronization mechanisms. So for example, like we have to include the atomic load or store, or the atomic increment decrement, or any kind of compare and swap. So this is all I would say some of the key hardware assisted synchronization mechanisms, which gonna also include test and set, we used to call TAS, compare and swap, and also fetch and add. This is the short term is FAA, which is a fetch and add. So then and like I would say some benefits for the hardware assisted synchronization. Of course, the benefits could be its performance, their simplicity, their scalability. These all are the benefits I would say for the hardware assisted synchronization. Then we're moving next to the optimistic locking. So this optimistic locking is concurrency control strategy which is used to manage the access to shared resources in a multi-threaded environment. So unlike pessimistic locking, which prevents the conflicts by locking the resources primitively, and so the optimistic locking allows multiple threads to access the resources simultaneously and only checks for the conflicts when the updating the resources. So for this one, and I would say they're gonna include some sort of non-blocking raids, multi-thread is gonna read the data concurrently without acquiring the logs. So the thread processed with their operations, assuming no conflict gonna be occur. And also it's the going to include some sort of conflict detection, their retry mechanism, and the advantages for this one could be its reduced contention. This could be the advantage for the optimistic locking, and the advantage could be its improved performance. Which like an improved performance, we're gonna lower the overhead compared to the I would say pessimistic locking, as logs are not held for long duration. So it's very much suitable for read a heavy workload where the writes are infrequent. And the benefit could be its scalability. With this one, with these the benefits, we have some sort of the disadvantages, the disadvantages is going to include retry overhead, their complexity. So these all are the disadvantages we're going to say in the we're going to face in optimistic locking. So this one, through this one, we're gonna see here the next slide, which is about the non-blocking algorithms. So, in non-blocking algorithms, actually a class of concurrent algorithm which is designed to ensure that the threads or the processes can operate without being indefinitely delayed by others. So these algorithms are very much essential for building the highly responsive and scalable systems. So they provides the guarantees about the progress and avoid many problems associated with traditional locking mechanisms such as deadlocks and contentions. So, the non-blocking algorithms gonna include log-free, wait-free, obstruction-free. So this is all the gonna includes in the non-blocking algorithms. So let's talk about some of its benefits. The benefits could be its avoidance of deadlocks, their improved performance and scalability, their enhanced fault tolerance. So this is the benefits of the non-blocking algorithms. So some common non-blocking algorithms gonna include compare and swap, load link, or the store conditional. This is all also the common non-blocking algorithms. Let's move next to the ABA problem. So the ABA problem is I would say a subtle issue that arises in a concurrent programming, particularly in algorithms that uses compare and swap for synchronization. So the problem actually occurs when a variable value changes from A to B and then back to A. This gonna making it appear unchanged to a CS operation, even though I would say it has been modified in between. So this gonna lead to the incorrect assumptions and potentially very much harmful I would say consequences in concurrent algorithms. So I have to explain how this gonna work, how the ABA problem is actually. For example, I would say, suppose we have variable x which initially has the value of a. So a threads the t1 which gonna reads the value of x and stores it in a local variable, planning to use cas to update its x. So this is about the I would say is an initial state. So through their intervening changes, this gonna includes while T1 is preparing to perform the CS operation, and other thread I would say T2 changes the value of x from A to B and then back to A. So the T1 actually appears that x has remained unchanged because it's still holds the value of A. And also in the CS operation, when the T1 performance performs the CS operation, which gonna comparing the current value of x, which is a, I told you, with its expected value, which is also a, and also proceeds into the updated of the x. So however, t1 is unaware that x was temporarily changed to b and pegged to a, which gonna lead us to the potential inconsistencies. So let's come to the next one, which is about the danger of spinning. So the danger of spinning, and the spinning also known as busy waiting. So it is actually a synchronization technique where a thread repeatedly checks a condition in a loop until it becomes true. So while spinning can be useful in certain low latency contexts, it can also introduce several significant dangers and also the drawbacks in concurrent programming. So some of the key problems with the spinning, it's gonna include some CPU resource wastage, and also some of the which gonna include the high CPU usage or the reduced throughput as well. So the next, I would say the problem with the spinning gonna include performance degradation, and also the thermal and power issues because of its increased heat and high power consumption. The problem could be its priority inversion, just because of its blocking the high priority tasks, and also the problem could be its inefficiency in high contention scenarios, which gonna be like contention amplifications as well. And how we gonna mitigate the dangers of spinning? We're gonna mitigate is through the adaptive spinning, through hybrid approaches, and also through by using the condition variables and the optimized spin locks. We're gonna I would say avoid the or mitigate the danger of the spinning. So this is about the danger of spinning, because while spinning gonna be effective like for short wait times or the low latency synchronization, it also gonna introduce some significant issues in terms of CPU resource wastage, performance degradation, thermal and power concern, priority inversions, and also the inefficiencies under highly contentions by using the adaptive spinning, hybrid approaches, condition variables, and also the optimized spin locks, which gonna help us to mitigate these dangers and improves the efficiency and responsiveness of concurrent programming. So this is all about today. If you got any question, then you please ask me. You have my email here, you can see. So this is all. Thank you so much. It was really nice to meet you, all of you. See you again. Thank you. Goodbye.